So this is our optimization problem. It's actually a simple optimization problem. It's a quadratic objective, okay, and a set of linear constraints, right. We already saw how to solve this. You guys did, right? Right, so you had a convex optimization tutorial. So one of the things that we are looking for from the convex optimization tutorial is that you will know how to solve this problem. Okay. So, right. So what we do after this? Write a Lagrangian, right? Right? Is that fine? One minus why? Take the minus 1 is greater than or equal to 0. I mean it's fine. I can do whatever. Right? So right. So I have to apply this for every data point. So I runs from I equal 1 to n. Okay. And I put a p there. So that's a primal. So we'll have to form the dual of this. The dual looks a lot easier to solve. Okay, the dual is actually a lot easier to solve. So we will go ahead and do the dual. So for first, I'll take the derivatives, right? So derivative with respect to beta, right? We can do that and solve it. We will get that derivative with respect to beta naught. Okay. So now it's where I am going to do some hand waving, but you can go through this computation. So take that, substitute into this, okay, and do a lot of simplification, right. So remember we have this beta squared here, therefore I am going to get a alpha I, alpha j, yi, yj kind of terms, right. So the dual will be so the dual is going to be a slightly simpler form. Why is it a slightly simpler form? So I have to only consider my constraints have become a lot simpler here, right. It's just going to be alpha I should be non-negative. Okay, that's all my constraints are. So it turns out that there are efficient ways of solving optimization problems of this form, right. You don't have to worry about it. I mean, there are lots of packages that solve SVMs for you. But then you need to know what the optimization problem you are solving, right. I don't want you to use it as a black box, right. So essentially what you are going to be solving is this, right. So when you have a solution, when you have something that is both primal and dual feasible, you can actually show that the duality gap is 0 in this case. So let's not go into that, but the point is, when I have a solution to the problem, right, it has to satisfy certain conditions. So already looked at that, the KKT conditions. If people don't remember it, please go back and revise that, right. So there are a whole bunch of things. So you need to have the solution to be primal feasible, right. You need to have the solution to be dual feasible, right. And so that essentially would have a bunch of things, right. Primal feasible would mean that well, your alpha i's have to be great, that will be dual feasible, right. That will be one condition. Yeah, these need to hold, right, because it's a solution for the primal, and then you have your complementary slackness, right. So that in this case becomes right. So I don't know if in the notes I think you saw it as lambda I fi, right. So this essentially that is it. So this is alpha I into fi, right. So this is my fi. So that's the fourth. Okay, these are the KKT conditions that need to be satisfied. Okay, and so what does this tell us? It tells us a couple of things. One, so we know what the form of beta should be. What is the form of beta? It has to be alpha I, yi, xi. Right. So it's essentially what you are going to do is your beta will be taking out certain data points from your training data, right, and adding them up. So suitably, I mean multiplying it by the output, the desired output. So if xi's output was positive, then this will be +1. If xi's output was negative, this will be -1. So you're going to take a few of those and you're going to add them up, right. So this should remind you of perceptrons. So if you remember, what we did in perceptrons is we took whatever was misclassified, we just kept adding it to the weight vector, right. So in some sense you are doing something very similar to that, but instead of having some kind of a heuristic approach to optimizing things, right. I mean we did do a gradient descent, right, but then we just said, okay, we'll arbitrarily pick the set of misclassified points and we'll do the gradient descent and so on and so forth. But here we started off by saying, okay, we'll minimize the distance to the closest point, and from there we derive something, and it looks very suspiciously like the perceptron update rule. Okay, in fact nowadays when people say I'm going to train a perceptron, they are actually doing this more often than using the perceptron learning rule. Okay, right, great. So now something else that you can observe. So this condition has to be satisfied, right. This condition has to be satisfied, right. So let us look at it. There are two terms here. So when will this be 0? When either this is 0 or that is 0, right. Is there some condition when this has to be 0? Sorry?
For the binding constraint, the dual variable should be 0. For the binding constraints, the dual variable should be 0.
For what constraints? Oh, okay, fine. But geometrically, can you give me an answer? Yeah, you are right. But for geometrically, can you give me an answer? So if this, when this has to be 0 is when this guy is not 0. Duh. Right? So when will this guy be not 0? When it is not the closest point. Right? If xi is the closest point, it will be bang on the margin. Right? For a point here, that term will be 0. Right? For a point here, the term will be greater than 1. Right? Or a point here, the term will be greater than 1. You see that? So since the term will be greater than 1, the term in the square brackets will be non-zero. So alphas have to be 0. Correct? So what does this mean? It means that points that are farther away from the hyperplane do not contribute to finding beta, because the alphas will be 0. right? Points that are far away from the hyperplane are not going to contribute in finding beta. In fact, the points that will contribute to beta are exactly those points that are on the margin. So in fact, for this data set that I drew here, right, there are only two important points, right, that one and this one, because only 2 points are on the margin, right. That makes sense. So such points which lie on the margin are known as support points or support vectors. Right, and your beta is going to depend only on the support points. What about beta naught? Okay, so we can plug in any data point here and you can solve for beta naught, right. One of the support points you can plug it in here and you can solve for beta naught, right. Which support point do you pick? Ideally all of them should give you the same answer, but usually it does not happen because of numerical reasons. So what typically people do is they plug in all the support points, okay, solve for beta naught and take the average, right. So each one in turn, right, for every support point you are going to get slightly different beta naught, you just take the average, okay. So that is how you compute the hyperplane. Right, at the end of it you basically have your yeah.
We can also have case when the point is on the margin as well as the alpha is 0.
Potentially.
That can be the case.
Uh-huh.
So would that point be called a support point or not?
So when would alpha be 0 if your data is on the hyperplane, on the margin? Sorry? Yeah, so that will be the one case when that happens. So essentially you have 2 points which are on the same things, not collinear but repeated things. I give you 2 data points that are on the same point, right. So by definition most of the support vectors will lie on the same line, so it can't be collinear, okay. So right, in such cases that could be the case, but yeah, these are generally degenerate cases, yeah. So yeah, sure, call them support vectors if you want, okay. Yeah. So one thing to note is my f hat right. So how is this going to look like now that I given the form for beta here? This is essentially going to look like I can flip these things around anyway. That plus beta naught, right? So if you think about it, I'll come back to this point later. So if you look at the dual, I only have x transpose x, right? And if you look at the final classifier I'm going to use, I'm going to have x transpose x, right? So if I have a very efficient way of computing x transpose x, right, I can do some tricks with this whole thing. We'll come back to that, okay? I want you to remember this. So any questions on this? Any questions on this? So before we move on, I just wanted to point out something. So if you think about how LDA works, right? So LDA tries to do a density estimation eventually, right? If you think about it, you make some assumptions about the probability distribution, the form of the probability distribution. What assumption would you make? It's Gaussian with equal covariance across all the classes, right? So that essentially means that every data point in your training set is going to contribute towards the parameters that you are estimating, right? So the betas you will estimate there will depend on all the data points that were given to you, whether they are here, right, close to the hyperplane, or whether they are very far away from the hyperplane, right? So all the data points will determine your class boundary. So that means that it becomes little susceptible to noise, right? If I have 1 or 2 data points that are generated through noise, right, even that will contribute to determining the separating plane, hyperplane, right? On the other hand, with this kind of optimal hyperplanes, we are only worried about points that are close to the boundary, right? So I can do whatever I want here, right? I can move a few points over here and things like that. It doesn't really matter. What matters is if any noise enters close to the boundary, right? So in some sense, if my noise is uniform, right, the LDA will get more affected, because even if noise inserts some points there, right, the LDA classifier will change, right? While my optimal hyperplane classifier will not move. It will be affected only by that fraction of the noise that changes the actual decision surface, right? Does it make sense? Having said that, I should point out that if your data is truly Gaussian with equal covariance, okay, LDA is actually optimal. It's probably optimal, okay? While this one will depend on the actual data that you get, but in general I would say that this is more preferable, because this is more stable. People remember what stability is, right? Small changes in the data will not cause the classifier to change significantly, right? So here small changes in the data will not cause it to change significantly in an expected sense, right? If I go and take the support vector and move it somewhere else, okay, the class boundary will change, right? But then I have whole bunch of other vectors which I can move around. Nothing will happen to the class boundary unless I move it closer to the hyperplane than the existing support vectors, right? If I take a point from here and move it here, of course the class boundary will change. So as long as I don't modify which are the support vectors, right, I will get back the same classification surface again and again, right? So in that sense, SVM, or we'll come to SVMs a little bit, this kind of optimal hyperplanes are very stable, right? Okay, so any other question? We'll move on.